Hello, my name is Krystal Garza and my mentor is Dr. Bruce Lee. I'm a mechanical engineering student at Texas A&M University Corpus Christi's College of Science and Engineering, and my research is development of a methodology to determine the efficacy of design variations in wearable airbag devices using finite element analysis. The methodology suggested in this study enables evaluation of the effect of expandability and shock absorption properties of the wearable airbag prototypes upon overall performance. The test results are to suggest optimum airbag volume and minimum airbag expansion trigger timing to minimize impact and protect the human body from falls, as well as the novel airbag design specifications to minimize air leakage and to manufacture an airbag material with high durability against external impact. The methodology will facilitate a way to optimize proposed designs without necessitating costly production of various prototypes in the planning and development stages. One of the growing problems as progress is made in the health sciences field are the elements of the growing elderly population. As people age, they become more susceptible to chronic disease, illness, and injuries, and are far less likely to make a full recovery due to decreases in bone density, skin elasticity, and mobility. One of the biggest health concerns in the elderly population is fall risk. The leading cause of accidental death in the population over the age of 85 and making up 70% of accidental deaths over the age of 75, the consequences of these injuries are severe. Not only is there a risk of death, in those who do survive, quality of life plummets, mobility and willingness to participate in enjoyable daily activities decreases, and the medical bills associated with recovery can be staggering. Annually, over $20 billion within the healthcare system is attributed to falls alone. The primary focus in the past has been on improving health and agility in the elderly, but these methods do little to benefit the user in the event that a fall does occur. Recently, the development of wearable airbag devices has taken off, and many companies have performed their own studies to determine the efficacy of their devices. Unfortunately, due to the nature of how new these devices are, standardized testing methods are just beginning to be implemented in studies and regulation is lax. Costly testing devices and the manufacture of prototypes has been the common method of testing these airbags. However, this can be expensive and the development, manufacture, and testing of prototypes is a lengthy process. This study proposes a method of preliminary testing to optimize the materials and geometries used before prototyping ever takes place. Through the use of finite element analysis using simulation software and experimental drop tests performed with a low-cost drop tower, the assessment of impact attenuation capabilities of wearable airbags can be analyzed, and accessibility can lead to globalization of a standard testing method. For this study, SolidWorks drop test simulation software was used. An assembly was created using modified geometries and an effective mass, the upper half of an adult's left femur, a model of the soft tissues at the hip, and the airbag prototype at full capacity. The material properties of these components were imported into the SolidWorks library and assumptions were implemented for the sake of ease of simulation. The femur model was treated as exhibiting linear isotropic behavior, and the material properties of cortical bone at the greater trochanter were assumed. The geometry was simplified to aid in the assembly of components, however, critical dimensions of the femoral neck and head were kept intact. Soft tissue was modeled using low-density polyethylene foam as recommended in various studies, and an 18 mm thick square foot of material was used to model the surrounding tissue at the hip. An effective mass was modeled using aluminum 6061, as the only consideration for this component was the applied load. For the airbag, the company that produced the prototype provided the material properties of nylon 6/6, and the thickness was modeled after a material sample of the textile used. An assembly using bonded connections was created, and a curvature-based mesh was implemented to perform the finite element study. The drop test parameters were set to an impact velocity of 3.4 meters per second at the lower plane of the soft tissue surrogate, and a preliminary drop test was performed while excluding the airbag part from the analysis. The location of greatest acting stress was obtained, and a probe was placed at the node to record a time history chart of the stresses acting at the specified point. 2 more iterations of the drop test were performed, one with the airbag included in the analysis and one without. The time history graphs were obtained for each at the sensor, and using the cross-sectional area of the femur at the sensor location, The peak impact force was calculated for each case and compared to the fracture threshold set forth in Madreca's thesis. For the experimental portion of this study, the testing device to be used is a drop tower whose design can be referenced in the diagram below. A drop tower was previously manufactured by Capstone Group Notorious ME and is currently being modified to implement linear bearings, which necessitated a change of materials for the drop plate from aluminum 6061 to steel. Bearing sleeves were manufactured using mild steel with a groove for C-clips to seat the linear bearings securely, and these sleeves were welded to the drop plate. An impact plate will be manufactured and attached to the drop plate with springs placed in parallel to obtain a stiffness of 47 kilonewtons per meter, and guide rods will attach the upper assembly to the base plate and run through the bearings of the drop plate. A Bertec load plate which outputs force signals to a computer will be placed upon a wedge angled at 12 degrees and attached to the base plate, which will act as a rigid target, and a surrogate hip assembly composed of an osteoporotic femur model manufactured by the Sawbones Company, an 18mm thick layer of low-density polyethylene foam, and the variable airbag prototype filled to capacity will be fastened to the base plate. Using accelerometers attached to the drop plate, a mass of approximately 28 kilograms will be dropped from a height to obtain an impact velocity of 3.4 meters per second. Force time history diagrams will be output and analyzed to determine the peak impact force acting at the femoral head, both with and without the airbag, and these values will be compared to those calculated from the simulated drop test to determine validity of finite element analysis as a reliable testing method. If validated, varying configurations of airbag designs can be substituted into the simulated drop test assembly, and the cost-benefit analysis can be performed as a time-efficient preliminary step to eliminate the need for costly prototype development. The simulation data obtained showed a peak impact force of 45.35 kilonewtons without the use of the airbag and 0.77 kilonewtons with it. With a fracture threshold of 3.47 kilonewtons, this data proves the usefulness of these devices. Experimental testing must still be performed to determine how accurate drop test simulations are as a tool to determine efficacy. Error within the applied testing methods can be attributed to assumptions of material behavior to aid simulation, simplification of geometry in both the airbag and biomechanical models, and assumption of no rotational movement in a straight fall. Although helpful in modeling, these are not realistic fall behaviors and serve only to analyze the force attenuation capabilities of these devices. Anticipated errors within experimental testing can be attributed to errors in manufacture of precision parts, small discrepancies in the placement of the biomechanical components, small variations in the geometry of the experimental models as opposed to the simulation models, as well as modifications which are not exact substitutes for the values set forth in the International Consensus Statement. For this reason, a large factor of safety should be taken into consideration to account for shift in placement of the airbag, unaccounted for stress factors, and frailty of the anticipated user. Due to unforeseen circumstances, the materials for the hip surrogate to be used in the experimental test were unavailable to complete the study at this point in time. However, progress is still being made, and an updated study should be available by late July 2021. As a final note, I'd like to thank Dr. Lee, the McNair Scholars Program, and the Division of Research and Innovation at Texas A&M University Corpus Christi for their generous support and contributions. Without their guidance and support, this research would not have been possible. Thank you.